Any questions from homework stuff? Yeah.
Can you come over? Oh, sir.
Huh?
Come over here.
Oh, this one?
Yeah.
Okay. That's on page what now?
Well, I'm not on the white book. I'm
Don't worry.
154.
I can handle. 154. Number which one?
15.
Oh yeah, okay. So the nice thing is everybody's got the same topics, no matter which book you've got. The other nice thing is, even if you ask a question in a book and somebody didn't have that book, it's good for them to see another example anyway with the help, right? And I'll bet you this problem is in the other book anyway. But this problem says I equals PRT. And this is solve for P. So this is where normally students are like, okay, solve an equation sucks, and then you're going to throw one at me that has absolutely no numbers in it. Math people, what the hell? Right. Everybody know what that formula is for?
Interest.
Interest, right? I always remember it as I be pretty. Right? Even if I'm not, it's just a way to remember. How do I solve this for, how do I get P by itself? Why is P not by itself? It's being multiplied by this other crap, so how do I get rid of that crap? Divide. So if you know how to solve equations, you definitely know how to solve these, because they're still just equations. Right? So if I divide by the stuff I don't want, then I'm going to be left with P. So to give another example, if I had a problem like A equals MW minus Y, and I want to solve for W, of course. And this is not just us trying to figure out how to fill your time. This is really actually crazy important, being able to manipulate equations with nothing but variables in them. Because right now, this equation is set up beautifully. If you know M, maybe M is mass, and W is something, I don't know, and Y is something. They describe a situation that I'm in. If I know all three of these, I can plug them in and A is right there. If I know M, W, and A, that sucks. Because if I had to plug them in and then solve, and then another one, plug them in and then solve, and another one, plug them in and then solve. I don't want to do that. I want to solve and then be done with the freaking solving. I don't want to solve over and over and over again. Screw it. I want to solve once, right? So if anybody's going into statistics, you're going to be doing a little bit of this, taking a statistics formula and rearranging it because you know some variables in some situations, and then others you know other ones. So how do I solve this for W? Where is the W? It's right there. Right, so it's really the exact same situation as that. These are the exact same problems. It's just here I specifically know what A, M, and Y are. Here I don't. Who cares? Solving an equation doesn't care. So the first thing I'm going to do is add that Y, just like I would first here add that 7. And what is A plus Y? Careful. Yeah, it's just A plus Y. If I say AY, I've made addition become multiplication. Yeah. And so I just love when I ask, what's A plus Y? People are like, pineapple. I don't know what the hell. So A plus Y is MW, and then one last step to get W by itself. Yeah, divide by the thing you don't want, because it's multiplication. Divide by M. Cool. This is a little unsatisfying to a certain degree because it doesn't come out with a number, but of course it doesn't. There are no numbers in there, right? You just have an expression that is more useful now. If you know A, Y, and M, it's more useful. Maybe. If anybody is at all interested in computer programming, you want to make a very strong computer program. You don't want the computer to be wasting time doing something like this 500 times, solving for W. You want to do it once, and then the computer, that's a lot of savings of time over time, right? Nowadays they make programs that are so stupid, so laden with shit that it doesn't need, because like, oh, processors are so strong. Anyway, most of you guys are like, shut up, Jeff, just keep but it irks me. I'm a little old man when I think about computer programs. All right, so anything else? Yeah.
On page 579, problem 72.
So this is back in the white book.
Yes.
Number what?
72.
Oh, yeah, okay.
They try to explain to me, but he just confused me.
Say again?
The
Oh, okay.
math lab.
All right. All right, let's see. So Brandon pays $4.95 a month. So for those of you without the white book, Brandon pays $4.95 a month for phone service, and they give a flat rate of 7 cents a minute. This is for international calls. Okay. Blah, 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 blah. 1 month, his total long distance phone bill was $10.69 for 1 month. How many minutes of phone calls, international phone calls, were made that month? So this $10.69 came from what? What do you have to pay no matter what? Yeah, $4.95 just to get you in the door. And how do you get to that $10.69 bill then? He wishes he could subtract. That would really suck. Yeah, you have to pay this much, and in addition to that, you have to pay 7 cents per minute. And so what's my unknown here? What's my unknown, of course? The minutes. Minutes is X. So how do I write that here? If it's 7 cents per minute, and I definitely talked for X minutes. So if I talked for 10 minutes, how much extra money do I have to pay? 70 cents. So I talked for X minutes, how much extra money do I have to pay?
7-ish.
Now here's where you got to be careful. If you write this, why is that horrible? That's $7 then, because this is already established that we're in bucks. So this has got to be 0.07. So he's got to pay this much money a month, no matter, even if he doesn't make a damn phone call at all. Plus 7 cents per minute. And that's how he got to $10.69. Now you can solve that for X. So this is a classic problem. It's like the plumber problem. You call a plumber, it costs him $20 just to come to your house, and then they charge you another $20 an hour or whatever. So it's got like a base amount plus an amount per something. That's a very classic algebra problem, because it's that per thing that we don't know. That's where a variable goes. I don't know how long he's going to be there. I don't know how long I'm going to talk on the phone, so forth. Yeah.
You subtract that 4.95 to the 10?
Yeah, now you just start solving this bad thing. So you subtract 4.95. I'll let you guys finish that out. It's not too bad. 2 steps and you're done. That should be the easy part. Solving the equation we set up. Yeah.
I'm having a problem with another word problem. 25 in the book.
On which page?
151. I'm sorry. 154.
154. Number 25?
Yeah.
All right, cool. Is everybody good with that here? Yeah. I always like to do a problem where it costs like $4.95 a minute plus so much for every additional minute to call the psychic. And the math student calls up to see what's going to be on the math test. Good old Dion Warwick says, hey. So 25 says a teacher has a salary of $25,920. For her second year on the job, that this is 4.2% more than her first year. So again, this is a the classic mistake people make is they take 4.2% of this and subtract it. And that is completely unfair. Because how do you end up at this amount? You would take our first year's salary and add 4.2% of that salary on top of that, right? So if I had, if I was making $10 an hour and they gave me a 20% increase, how much money am I making now an hour? How do you figure it out? You take 20% of 10, which is 2. So you take 20% of 10, which is 2, and then you add that back on to 10. Now watch this. If you take 20% of 12, what's that? Trying to work backwards. So like, okay, 12 is 20% more than I was making before. Well, what's 20% of 12? 240. If I subtract that, I'm going to get below what I should have had last. That's not right then. I can't take 20% of this bigger number. I've got to take 20% of the number I had before. The hard part about this is I don't know what the hell I had before. So the amount I made the first year is X. So how do I get to 25,920? I take what I was making last year. And yeah, good.
Plus 4.2.
Yeah, plus
0.
4.2% of that amount. And how should I write that here so math understands? 0.042 x. Good. So that's what I was making last year, increased by 4.2% of that, gets me to the second year. That's basically almost the way every single percentage problem that's kind of backwards. You don't know what you had before, but you know what you got now. That's what they're almost always going to. If this was like a decrease, I would have put a minus there. Maybe. Some people like this. If I increase by 4.2%, if I increase by that much, what percentage of my salary from last year am I making now? So let me say this a different way. If they decrease my salary by 4.2%, what percentage am I at now? If they decrease my salary by 4.2%, what percentage am I at? I'm not at 100% anymore. I'm now at 95.8%, right? So think about it the other way. If they increase my salary by 4.2%, I'm now at 104.2% of what I made before. And so this should be 1.042x is what I'm making now. And what's the next step on this? What's x plus 0.042x? 1.042x. So some people are able, and it makes more sense for them to go to this like second step, to start here. If that makes sense to anybody, that's not a bad way to do it. If that doesn't make a damn bit of sense to you, do it this way. If neither way makes sense, come see me. The problem here, of course, is I don't know the number that I apply the percentage to. I can't apply the percentage to the after effect. That's not fair. That is not the same as what this was applied to before. It's never going to come out the same. Okay. So we saw that in the white book is number 74, that plywood problem that we did the other day. All right, so anything else from homework? Yeah.
And my book, 60.
In 9.2?
Yeah.
Okay. That's the one with all the fractions. Right? And the inequality? No? Yes? Yeah, okay. Alright, so the nice thing about inequalities is they're only different from equations in one true way when you want to solve them. You got to be careful when you multiply or divide by negative. Other than that, everything's the same. So if I have an equation with fractions in it, I can kill those. Bless you. So if I have an inequality with fractions in them, I can kill those too. how would I kill those fractions if I wanted to?
That's it.
Yeah, multiply by the LCD. Cool. You don't have to. You could, of course, work with the fractions, but when given a choice, I am not going to. Right? So there's two things there. You got to know how to do it. If I force you to do it, you got to know how to do it. But to be smart about it, I'm not going to do it. I'm going to do what I'm allowed to do. I'm going to get rid of my fractions. So what is the LCD?
36.
You know, all kinds of things. Can't be 12 because 9 doesn't go into 12.
36.
Yeah, it pretty much has to be 36. Notice that this could be reduced. Right? But that won't really affect my LCD anyway. So if I multiply by 36, everything. Is it pretty cool being able to do that? Yes?
I do it like you multiply the bottom by
Yeah.
2.
I like it.
By
Cool.
12, and then the top by, let's say, 4, and then the other one.
I love it.
Can you do that too?
Certainly. In fact, give me 1 second, and I'll show you how this is exactly what I'm going to do anyway. So what she's saying is, how would you make this have a 36 on the bottom? Multiply top and bottom by 12. 12, right?
Yeah.
Well, 3 goes into 36 12 times. So I'm going to multiply by 12 anyway, either way. They're both kind of different ways of looking at it. Right? So one way to do it is to multiply by the LCD all the way through. The other way to do it is to first make everybody have that LCD. So here I would multiply by 12, 4, 6, 9. So then everybody would have 36 on the bottom, right? And then you multiply by 36 and it cancels everywhere. So this is kind of the same thing, just reverse. I first multiply by 36 and then I end up with these numbers that are going to multiply by the top. So either way works. If you like this way though, I love it. You know why? Because it'll work. Yeah. But I'm trying to show you how both ways are the same, but they are a little bit different how you look at it. So if you want to do it this way, kick ass. So let me just catch up to this way. You can keep going this way. Let's see if we get the same thing here. 9 goes into 36. 4 and 6 goes into 36. 6, 4, 36, 9. So I get 24t plus 32 greater than equal to 24 minus 9t. So I get the same thing either way, of course. Yeah. So either way you like to do it works. I'm allowed to do this because I have an inequality that has two sides. So I'm allowed to multiply, subtract, add, divide by whatever I want to. Except 0. And now you just start solving this thing. So you move your t's over. Move your 32 over there. Is that cool? I mean, this should be the nice part now. We got rid of all our fractions. This should be pretty good. What's the last step?
Divide by 32.
Divide by 33, and what do I get? Good. Don't flip that around. I don't care that's negative. I divided by a positive, so I don't change the sign. That's gross. So if I have to graph it, all I care about is the fact that negative 8/33 is between what two numbers? Negative 1 and 0. So there you go. Put your negative 8/33 here. And which way am I going to shade? This points you in the direction. As long as your variable's on this side, the inequality symbol points you in the direction. That's silly. Right? I wish more math did that for me. Which way, math? This way. Okay. So I'm going to shade up, and what symbol is going to be on here? Bracket, because I'm allowed to equal, so I want to include it and a shade up. So then interval notation will basically look just like that. From negative 8/33 up to infinity. From negative 8/33 inclusive up to infinity, and of course you never include infinity. Some of you guys are like, You sure you're feeling okay, Jeff? You wanted to go home? I'm all right. Yeah. Which way to shade? So two things. I know I shade up because this says the answers have to be greater than or equal to this. And where are the numbers that are bigger than this? That way. The shortcut is, which way is that pointing? That way. That kicks ass. So if it was less than, it's actually pointing that way, isn't it? As long as your variable is on this side, that will point you in the right direction. In the correct direction. Okay. Yeah.
I hate those word problems where they say 3 less than the sum of 2 and some number is 6. What's the number? I get super confused with those. It's on 578.
Yeah, I got it. So in section 9.2, number 63.
Yeah.
Did you have anything else about that? Everybody got this here? Okay. Poor little word problem. You hate it and everything. So let's see, 63. 3 less than the sum of 2. 2 and some number, I like that, is 6. Okay, right there. So this is an English statement that I can translate directly into mathematics, right? The one thing you've got to be careful about when translating expressions, statements, is the less than thing. 7 less than 10 is 10 minus 7. So 3 less than this is this minus 3. So I know the minus 3 is going to be there. I know it's going to equal 6. So now I just got to put here, I got to put this thing. The sum of 2 and some number. Yeah, 2 plus some number. So some of you guys put 2x there, but that wouldn't be the sum, that would be the product. I love it, which would mean multiplication. You guys got it with me? So 3 less than what? The sum of 2 and some number is 6. So that's how you put that together. And then you just got to solve that. Yeah.
Would x plus 2 be wrong?
No, it would be fine.
Okay, that's what I did.
Sum is okay. Sum, you could do it, of course, either way. If it's a difference, it must be the way it's given to you, because when you turn it around, it's not the same number anymore. But sum, you could put 2 plus x or x plus 2, because who cares which way you add. Yeah. But if it's a difference, you got. If it said the difference of 2 and some number, it's got to be 2 minus x, because x minus 2 would be different.
Can you do 66 too?
Is this okay?
Yes.
And then you just solve that, right?
The sum of 3 consecutive integers.
Oh yeah, good. Now this is the question I expect. So there are certain questions I expect, and if I don't get them, I get a little worried. So this is one I expect, right? And again, this is still in the white book, but it says the sum of 3 consecutive integers. Okay, not even integers. The sum of 3 consecutive integers is 195. Find the numbers, right? So what the hell? There's a shortcut to this, but I need to see the algebra, right? How many players do I have in this problem? You can pretty much attack almost any word problem in the same manner. What are the players? How do they relate? That leads to my equation, right? So how many players do I have? Obviously I have 3. So what are they?
X.
No, but don't go there yet. In English, the first number,
X.
second, third. Alright. So the first number, do you know what it is?
X.
I like it. That's the appropriate answer. Not, I don't know, but it's X. The next integer, now give me an integer. I'm going to give me a number. 3. What's the next integer? What's the next one? What do you keep doing? Add 1. So if the first number is X, the second number's got to be
X plus 1.
X plus 1. And the next one's got to be x plus 2. Now, here's the neat thing. If I would have said 3 consecutive even integers or odd integers, every set of... give me an even number. 2. What's the next even number?
4.
They're 2 apart. So if I had 3 consecutive even numbers, the first one would be x, the next one would be 2 more than that, and the next one would be 2 more than that. Here's a freaky thing. When I say odd integers, people think it's different, but no. Give me an odd number. 3, I love it. What's the next one? They're still separated by 2, aren't they? This would work for odd or even. Odd numbers, even numbers, they're always separated by 2 to go through them. This one just said integers, so I just want 3 and then 4 and then 5. Right? So what are these 3 things supposed to do? Add up to be 195. So then you can solve that. Yeah.
So the problem was said the difference instead of the plus sign would be like x minus 1 and x.
They'd have to be a little more specific. They have to say like the largest one minus the smallest one or something. They could once they set up 3 consecutive integers, they could say like the middle one is actually twice the first one minus 8, or they could do whatever they want to, and then just write exactly what they said in that. Yeah.
Don't the x plus 1 and the x plus 2 have to be in parentheses?
They could be, and I appreciate why you're saying that, because then you can find all 3 of your parts. But of course, there's an understood 1 out there, then I could just take them right away. They wouldn't change the math. But it is a way to make sure you got all 3 numbers, and you can see them, all 3 of them. Yeah?
9.3.
Everybody cool with that one? All right. We keep going. I'm going to do all the homework for you. So you guys are like, he's on to us. Number 12?
Yeah.
Oh, yeah. All right. So typically, when I give you an ordered pair, okay, it makes sense. It's a pair of numbers, and the order matters. Right? That's why it's called an ordered pair. If I tell you like 2, 5, what does that 2 stand for? X, and the 5 stands for
1.
Now, if I have any other variable, let's say P and Q.
X1.
I have P and Q, and I have like P plus 2Q equals 7 or something. The point that it has, because X and Y are just dummy variables. I desperately want you to understand that. At some point in history, they just decided we're going to use X, and then if we already got X, we'll use Y. And if we already got Y, we'll use Z. Right? And then if you go to 4 dimensions, you use W. Freak. But in the problem, it could be peas and quail. I don't know. So I might not want to use X and Y. I might want to use letters that represent the problem. If it doesn't say this point is always in alphabetical order. So the problem says this: C equals D plus 1. And they say, is this a solution? 1, 2. So what does 1 represent?
C.
C. It's got to represent C. They don't say otherwise. So I must assume it's alphabetical order. So the 1 goes in for the C, the 2 goes in for the D. So if I do that way, this thing goes to hell, right? Which is fine. So you say not a solution. The evil thing about this problem is if you make a mistake and do it the other way, it works.
Yeah. That's my question.
So they're trying to make the point there. They don't say it's alphabetical order, just like X, Y. If they don't say the variables they're using have to be in alphabetical order. You guys with me? It just kind of standardizes everything so everybody kind of knows the way they better set it up and the way to interpret things. Right? Yeah, maybe. Yeah.
I just want to know how to use a graphing calculator.
Oh, I'm glad you're saying that. There was a problem. I tried to skip over those where I could, and I think there was like number 18 and 21. You could do those by hand or just skip those. So if I assign something that references your graphing calculator, a graphing calculator is not required for 103. But if you're curious how to do it, I could show you. Depending on where you're going next from there. Well, 160, you're not going to really need to graph a lot. So that's why 103 doesn't lead you to the places where you got to use it intensely. 110, we'd be using the hell out of the graphing calculator just to get you ready for pre-calculus, which is what I call graphing hell. Right, so just to get you ready for that. 103 doesn't lead to anything intensive, so if you have one, I could show you how it's done. If you don't, I don't want to freak you out or make you feel like you're not a part of something. Is that cool? So the problem, I think it's 18 and 21. I think it's in the white book.
Yeah.
Yeah, section 9.3.
Can we skip it?
You can skip it.
Thank you.
It would make my day if you try to graph it by hand. But if you skip it, I'm not going to hate you.
So, would graph it by hand mean like?
Just start making an XY table.
Okay.
And we should, at this point, we should know what something like this is going to look like. If it has a 2x squared and an x and a number in there, whatever, what is that going to look like fundamentally? It's going to look like a U, right? A parabola. Have you guys seen that before? Yeah, and it's positive here, so it's going to be up. So it's going to be a parabola. It's just going to be somewhere, who knows. So I make an XY table so I can see where the hell it is. This one you might not know possibly, but, I mean, this one's a little freaky, to tell you honestly. This one you got to be careful about.
Doesn't it go side?
Hmm?
Doesn't it go?
A circle, not quite.
No.
Yeah. But I mean, this one you can plug stuff in. What's got to not happen inside here?
Negative.
Can't be negative, but it's never negative, is it? If you think about it. The only way this could be negative is if it's below 0. This thing can't even be 0. What's the smallest x squared could possibly be? Using real numbers. 0. So the smallest the inside could possibly be is 1. So you actually can use all x's. So you just make an xy table and do -3, -2, whatever. Right? And then 0, 1, 2, just plug some values in and you can kind of see how this is shaped. But again, if you want to skip it, I'm giving you the option to skip because it asks you to use a graphing calculator and that's not part of this curriculum. Cool? Okay. But we're using the same book in 110, so it will be sprinkled throughout. Hopefully I've skipped the other ones later. Okay. You guys doing all right? Okay. Tell some of you guys we're hoping for a long weekend. Jeff, you're okay, dude, but please be sick again. All right. So I think that's enough of that. Let's get into some new stuff. Oh, real quick, before I forget. You guys here today, Lucas Garcia and Eric. Anybody not get that warm-up sheet that we did the first day? Anybody not get that back? Because I have one without a name. Oh, if you did it, yeah. Anybody not get that back? Okay. What I'm doing right now is try to keep things straight for you guys. So I'm getting into 9.4 in the white book, which should relate to 4.1 and 4.3 in the blue book. Okay. So it's about systems of equations. Yep. And we will be getting into factoring today and all that kind of stuff too. We're going to try to finish out the first section, the algebra review. Yeah. Oh, section 4.1 and 4.3. I think the homework I assigned was from the review section. So it's page 281, starting. But here's the idea. If I just put that up there, how many answers are there?
2.
Try again. What does each answer look like? Give me one answer.
Y equals.
No. Give me an answer. Give me a solution to this. I like it. Every solution has to look at like a point because it's made up of two variables. Cool. Y'all with me so far? Okay. So how many solutions are there? A lot is a decent answer. 3 is not a good answer. Every single number you can come up with for this, isn't there a number that would make it work?
Yeah.
I mean, obviously, if you made this 3, this is 3. 4, this is 2. Right? Yeah, if this is 10, this is negative 4. If this is 1,000, this is negative 994. You with me? If this is pi, this is 6 minus pi. If you want to get really freaky. So every single, all right, let's try this again. How many answers are there? Infinite number. Okay, good. And this is why we graph these kind of things. Because if I ask you for all the answers, the quickest answer is, here's a graph, Jeff. When I draw that line, every single point I go through is an answer. To list all the answers, of course, would be stupid and insane. Right? You'll be in a little rubber room, just writing on the walls. And then this, and then this. I'm almost done. So the problem with this, really, if I ask you for it to solve this, it's kind of a silly question. It's not restrictive enough. X and Y could be a lot of damn things. Right? So it's sort of like me saying, all right, I am twice as old as you are. Tell us how old each of us is. You guys are, I can't. You haven't given me enough information, right? There's 2 unknowns, and I said one thing. So if I give you one more piece of information, together those somehow should come up with a single solution. There can only be one, or possibly, there could be one answer to this. This is called a system of equations. So it's equations that all have to be true at the same time. So the most fundamental way to answer this, and what turns out to be the kind of craziest way to try to answer this, is to graph these two. In this case, I made nice ones. Can we graph those two? What's the quickest way to graph? Yeah, good. Solve for y. So we can graph those two, right? Is that cool? How do I graph this first dude?
0.
Good. The y-intercept is 6. It's always the most exciting part. So the y-intercept is 6, and then it says go
1 down.
down 1, over 1, down 1, over 1, down 1, over 1, down 1, over 1. Okay. There's a reason I'm going more than normal. Because now I know specifically where all those points are. Now come on top of that and do the other. What's he got? Yeah, negative 4 is the intercept. And then I go...
Up 1.
Alright, Jeff, that's enough of that. Now, supposedly, this would line up. Yeah, okay. My scale just sucks. Okay. So if you're very careful with your scale, and you're very careful with counting over more than you normally would. Because you can imagine, if you don't count over very much and you draw a line, I'll bet you anything it's not going to be straight. And then you're going to draw the other line, you're going to be like, that looks like 1.7. No, screw that. Right, if I just count more, I can kind of see where the points line up with each other. What's the answer? Who?
0. 1, 5. 1, 5.
5, 1. Cool. 1, 5 would be up there. Cool. Okay. So you can see why it's important to get the order right, because now 5 minus 1 is 4, but 1 minus 5 would not be 4, so you got to be careful. So the answer to any system of equations will be a point, or possibly more than 1 point. We'll see that later. You guys kind of with me so far? This hopefully should sound familiar. This is still part of the review. So one way to solve a system of equations is graphically. You can see why this way would suck pretty quickly, because what if the answer was actually 1.4, 2.897? I am not going to see that. I can approximate it, but there ain't no damn way. I have trouble getting the answer 5.1 from my ugly scale. I'm not going to get 1.7, 2.89, whatever the hell I just said. right? You guys kind of with me? So I want an algebraic way to do this. Everybody got this here? Okay. So the algebraic, there's two algebraic ways to do this. Anybody know what those two are?
Substitution.
Yeah, so this is graphically. The two algebraic methods are substitution, I heard that,
Elimination.
and elimination. Good. So if you want to use substitution, let's see. The way that substitution works, I want to use both pieces of information. The big problem is, inside either piece of information, there's two unknowns. So I always feel like this is a detective trying to solve a murder mystery, right? So normally you can't solve it by finding one piece of evidence. You have to find several, because there's a lot of shit you don't know going in, right? Because you weren't there, unless you did it. So to use the substitution method is the more subtle way of doing things. It says, take one piece of information and solve for a variable. So how do I solve this first one for y?
Y,
We already did it, didn't we?
y equal minus 6 plus 6.
Yeah, 6.
Minus x plus x.
I like it, cool. And then I can use that. So I know y is 6 minus x. I know that. So now in the second guy, he says x minus y, but I know that y is 6 minus x. So that's why it's called substitution method, because you just substitute the information in. So then you get 2x minus 6 equals 4. So x, add 10, add the divided, 5. Yes, ma'am.
So what happens when, like, let's say your answer is a fraction? How do you, like, I always forgot to do that. Like, let's say it's x over, like, 5 thirds. And then you plug it into the...
Yeah, you just have to deal with it.
So you just multiply the bottom by the side and then add the top?
If one of your variables is a fraction, you have to plug it back in to get the other one. You just have to deal with the fraction.
And then you times it by...
If you want to. Whatever you got to do to solve it, that's what you do.
So you times it by... How do you times it again? I forgot.
Well, we'll do an example of the fraction next. I got x is 5. Now, of course, I know I'm not done. Yeah.
How did you get number 2?
Yeah, I can do it.
All right, so the first equation I solved for y, you with me? Now, if I plug that back into itself, I'll get x plus 6 minus x is 6. Well, yeah, it is. 6 equals 6. But that's circular logic. I'm twice as old as you. You're half as old as me. Thanks, Jeff. That helps. I just said the same damn thing twice. I can't plug it back into itself. It's never going to get anywhere. I've got to solve one, plug it back into the other one. I want to use both pieces of information to figure this out. So from the first one, I know that y is 6 minus x. I know that's true. I plug that into the second guy, and notice how this is why I call it the subtle way to do things, because now how many variables are in this equation? I know there's 2 x's, but there's just one variable, x. You with me? So you can solve it then. The problem with solving this is there's 2 freaking variables in that thing. Now I've got 1. Okay, I can solve that, right? Okay, and again, this should be review. But if you can't, if it's been a while, I understand. So the problem is, am I done yet? Because I know my answer's got to have 2 parts to it, the x and the y. So the cool thing is, the first guy tells me y is 6 minus x, so y is 1. If you stop there and circle those answers, I'm happy, but I'm even happier if you make it an actual point, because that's what the answer always is, it's a point. Okay, yes, sir.
Can we solve this problem with the addition?
Of course, that's the second way. We'll do that. I call it the elimination method, because that's, you want to kill a variable. Yeah. That's the way I prefer myself. So the second way to do things, and then we'll do some fraction problems. Looking at the same problem, I could do it elimination method. So I've got x plus y equals 6. X minus y equals 4. So elimination method says, all right, I've got to add the same thing to both sides of an equation, right? So if I add 6 to 4, that's fine, as long as I add 6 on this side also. Let me just stop there for a second. So if I add 6 to this side, I better add 6 to this side. But what's 6? 6 is x plus y. That's why I'm allowed to just add equations directly. I'm allowed to do that because I am adding the same thing to both sides of the other equation then. And the reason I want to add these directly is what's going to happen. Y is going to go away. So this was a very sneaky way. It kind of snuck something. Okay, y, get out. It kind of snuck another thing in place of y. That's much more direct. It says y, die. Right? When you add these together, I get 2x. Those go away. X is 5. And then you just plug it back in either one of them to see what y is. Yeah.
So let's say that one ends up being like 5 over 1, then that's the x one, and then the y could be just like, it doesn't matter, the x is like a fraction and the y is like a 4 or something? It
doesn't matter because that could be true. I mean, two lines could meet at any point. So one part of the point could be a whole number and the other part could be a fraction. One part could be a square root and the other part could be, who knows. Yeah. Cool. Yeah.
You can only use that though when you can cancel out one of the variables, right?
And you always can if you adjust things. So I like to look in your face. So then here you'd say, okay, I plug back in the first guy. If I plug a 5 in, I get y equals 1. Thank God. Cool. Once you get one variable value, you plug it back in anywhere, you get the other variable value. Okay. So two things I want to do here now, real quick. I want to deal with one that's got a fractional answer. Oh, I can probably do both of these at the same time. So if I'm not careful with how I set a problem up, the answer should be fractional, right? So let's see. Let's see if I get lucky but unlucky. Okay, so I've kind of jumped to a much more difficult problem, but the idea, this is the hardest part about mathematics, is to realize if I understand the idea of what I want to happen, what I have to happen, I have to memorize a lot less. This is not any different from that, really. First off, do I want to use substitution method here? Because that would be even worse. I would get a whole bunch of frickin' fractions running all over the damn place. No. Let's not do that. Because I can't solve for any of these variables without creating fractions. You guys see that? Nobody has a 1 coefficient. Okay, good. So let's use elimination method. Your question is, Jeff, man, you can't use elimination method because no variables go away. So what do I do then? How do I force a variable to die? Yeah. And it's the same idea as LCD, really. These are already opposite signs. So what's the LCD of 2 and 3? 6. So if I multiply this guy by 3, and this guy by 2, those go away. And then I get 23y equals 39. And as promised, if I'm not careful, I get beautiful stuff like this. Right? And this could certainly happen to you in your homework, or, I don't know, in a quiz or a test. So what's wrong so far? I mean, what do I have to do now?
Now you have to plug back in.
Yeah, now I got to figure out what x is. So you get to pick whichever one of these you want. I would say maybe the first one. I don't know. And I got to plug that in to figure it out. 2x plus 3 times y, but y is 39/23. And I mean, this is uglier than you'd hope, but this should not make you go take some medication. This should not be that big of a deal, right? And I don't want to see decimal answers here. Screw that. Work with the fractions. So 2x plus 117. 3 times 40 is 120, but I got 39 threes, so 1 less 3 is 117. That's how you
So
multiply
you
quickly.
multiplied
Yeah.
23 and 3 and then added the answer to 39? How did you get 117?
Definitely not. This does not mean 3 and 39 23rds. This means 3 times 39 23rds. So how do I do that? 3 times 39. Do I just multiply across? So there's this notation here sucks because it actually means this. You guys with me? That's what that really means. That's why, how do you make this into an improper fraction?
22 over 7.
How do you make it into an improper fraction? 7 times 3 plus 1, right? So why does that work though? Because how would you add these two?
LCD.
Yeah, LCD. What's the LCD? It's always going to be this, isn't it? Multiply by say, there's the 7 times 3, there's the plus 1. Right? So that whole thing is a shortcut. But that is very different from this. What does this mean? That's 3 sevenths, right? That's 3 times 1 sevenths. That's one of the more evil things that students don't seem to have too much trouble with it, but every now and again it's like, oh shit, that's right. So here, what's the next step? Subtract this ugly thing. So how do you subtract that? LCD, right? And again, this is not as nice as you'd hope it to be, but it's nowhere near as bad as to go to the next problem and not finish this, right? So I've got 2x equals, what do I have to do here to get LCD? Multiply by 23, right? So 23 times 11. Yeah, I don't know what it is. 230. 253. Yeah. So 2x equals 253 minus 117. 136. And then divide by 2. Here's a really cool thing. You guys kind of with me so far? This is not that big of a deal. Everybody has a slight aversion to fractions. I understand that. But if you have to deal with them, you should be able to. Right? This is the worst kind of thing that could happen in these problems. Because the graphical substitution elimination methods, people normally are pretty good with those. The worst thing that could happen is you have ugly numbers to work with. But that's not that bad. When I divide by 2, I multiply by 1/2. That's probably the easiest way to deal with things that are already fractional. I'd rather look at that than this, is what I'm trying to say, right? Division by 2 is multiplication by 1/2. So then you can just reduce. 2 goes in at 136 68 times. So I get x equals 68 23rds. So my answer is, of course, 68 23rds, 39 23rds. That's awesome, Jeff. That's the worst thing that can happen to you. Do you understand? And that really should not be that bad. And I do not want to see decimals here. Yeah.
Can you go over that, just the last step again? I see where you're, the top 2x equals 253, and then, so right below there.
So then I just subtracted these, right?
Uh-huh.
And then I divide both sides by 2. Division by 2 is the same as multiplication by 1/2. Just makes it a little easier to look at. Rather than making this over 2, that's just disgusting. And people almost always make mistakes when you write it like that. That's a kind of nice thing to remember. If you divide by 7, it's the same thing as multiply by 1/7. So if you already have a fraction there, I'd rather write it like that. It's easier to look at then. Okay. Don't think every problem's going to be this way, right? This is the worst thing that could happen, and it might not happen to you at all. I don't know. I don't think they're going to do that kind of thing to you a lot. So here, you guys try this problem. Everybody got this here? This side here? Yeah. You guys do this problem. That should come out nice, just to let you know. this, so it's 3 over 1 times this. 3 times 39 is there, 1 times 23 is there. Yeah. Cool. So it's not 3 and that, it's 3 times that. Yeah. True, you need to do it. Yes. Yeah, yeah. Yeah, kick ass. Alright, y equals -2. Because 41 goes in there too. 41 goes in there twice, yeah. So that's a lot better. That, yeah. 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 Beautiful. Okay, so you cannot, these two equations are what you're given. Those two equations are both true. You can't use any other equations except for these two. So why am I saying that? If I want to kill the y's, I can't just multiply this by 7 and this by 2. I have to multiply the whole equation to keep it the same equation. You with me? I know I only want to deal with that, but my world is, oh shit, I have to do the whole thing to make something happen here. Otherwise, I have a whole different equation. My answer is going to be for a different problem, which sucks. So here, these two are already opposite. So I saw several people doing the y's, but if you wanted to do the x's, you could just multiply this by 3 and this by -5, because you want them to cancel, right? But let me do the y's. If I multiply 1 by 7 and 2 by 2, right? So this will be 35x minus 14y equals 7. Double this, 6x plus 14y equals 34. And now when I add those, 41x equals 41. That's awesome. So x equals 1. And the minute you have one variable, you just got to plug it in either place to get the other one.
X, y equal to.
Yeah, me too. I got 2.
That's fine. So what you guys did, let me finish this way out real quick. So if I plug a 1 in here, and then I can solve real quick, 7y equals 14, so y is 2. So I eventually got there, right? So what you guys did instead was you multiplied in a way that would kill the x's, right?
Yes.
So if you multiply this one by 3 and this one by negative 5, you'll have 15x minus, no, it's 3, Jeff. Yeah, 6y equals 3. And then negative 15x minus 35y equals negative 85. So then your x's go away. You get negative 41y equals negative 82. And thank God 41 goes into 82, so you get y equals 2. And of course when you plug it back in, you're going to get x equals 1. So it doesn't matter which variable you get first, because that's going to get you the other variable that you need. Yeah.
So I get to there, and then after that, I don't know what to do.
Once you know y is 2, you can plug that back into either one of these to figure out what x is.
It doesn't matter what it doesn't matter?
It doesn't matter. Why does it not matter? Because I'm finding the point where these two equations are equal. So that's actually a quick check. If you plug 2 back into both of them, you better get the same number out. That's really where are these both true at the same time? So that's why it doesn't matter which one you plug it back into. Good.
And in substitution, it would actually matter which one you plug it back into, right?
Not really. When you do substitution, you will always have, we had like that first one was like this. You'll always have one equation solved already.
Oh.
I could have used the other equation, but that would have been kind of silly because I've already got the one that's solved already. Does that make sense? So substitution method, you always have one equation that's solved. It still doesn't matter which one you use. It's just kind of like, well, why wouldn't you use the easy one? Yeah. This one is like, it's almost a coin flip, right? Which one to use? Okay. I got nothing more to say about that. So that's section 9.4. Section 9.5, I'm going to do polynomials real quick. I'll see if you guys want to break. And then we're going to jump into factoring. Cool? Okay. Alright. So, in general, I'm not most concerned about definitions and terminology. But I got to be careful when I say that because they are still important. It's important to understand what I'm saying when I say it. So there's a lot of terminology that goes along with polynomials, and the very first one, of course, is the word polynomial itself. What the hell does that mean?
It's 2.
More than that. Many terms, right? So just strictly translating, it means many terms. But what does it really mean in mathematics when I say I have a polynomial that I'm working with? One thing it means is I should be allowed to plug in any value I want. And really the reason that is because the way this is defined. A polynomial is any collection of terms with number coefficients and variables to a power where no variable is to anything except a whole number exponent. Let me say it again. So you can only allowed, let's go right to the chase here. Only allowed whole number exponents on your variables.
So there would be no fractions, right?
That would be no fractions with variables on the bottom.
Oh, I see.
Yeah. So here's an example of not a polynomial. 1 over x plus 2. 3x minus x to the negative 3. 4x cubed plus 6x squared minus 7x to the 5/8. Those are all not polynomials. And really one reason why we do this is because can I plug anything I want to in here? What value can I not plug in? 0, right? What value can I not plug in here? Still 0, because this would be 1 over x cubed. It can't handle 0, right? This one is actually more because of the shape. Polynomials have to be smooth and continuous. fractional powers very often have some kind of a cusp to them, believe it or not. So a polynomial can't have something like that. Wow. And there are functions who have that kind of thing happening. So, just to make it real clear, the most important thing is the fact that a polynomial, you can plug in any value you want to. Because part of the definition is it can't not be that way. I can't have any variables on the bottom. You with me? Also, I know that the shape of it has got to be smooth and continuous. Maybe. So a very basic example of a polynomial is what's called a quadratic, a squared. Right? So this would be a quadratic. So you guys remember the good old quadratic formula, right? They involve x squared kind of equations. You with me? And then you have a cubic, which would look like that. It looks like a quadratic where half of it fell out. Had an interesting evening. You wake up and half your face is like, "Arr." Right? A friend of mine calls this the giraffe graph. One of my colleagues here. But I always thought that was evil because it's a giraffe who's had his front legs cut off. I'm like, boy, that's kind of evil, man. Giraffe graph. We're just going to fall over. But, whatever sticks in your head. Right? Are we guys a little bit cool? Give me some examples of polynomials.
X squared plus 5x minus 3.
Cool. Specifically, that is a trinomial. Like tricycle. It's got 3 terms. Bless you. Give me another one. Or don't. All right. You guys don't want to play along. X squared minus 81? That would be a binomial, like a bicycle. So let me give me another one. Eddie.
X to the third.
Stop. Okay. Well, that would be a monomial. Like monocle. Monocle is a single lensed glass, right? So that's monomial, one term. And anything over that we just call polynomials. We don't start going crazy with the quadrinomial and quintinomial. No, thank God. You guys semi with me? Alright, so that should all be review. These are all polynomials because the variables are all 2 whole number powers. Here's another polynomial that you might not realize is a polynomial. 11 is a polynomial. Does it have any variable that's not to a whole number? No, in fact, the variable it does have is to the first whole number. It's got how many x's? 0 x's. There you go, so that's fine. Any number is automatically a polynomial. That always freaks people out. But this is a monomial. If a number can be a part of a polynomial, it should be allowed to be a polynomial by itself. And it is, thank God. So the next idea is the idea of degree. I'm going to go a little quickly through this. It should be a review. The degree of a term, and let me show you, let's make a little more interesting polynomial. All right, there's a binomial. It's got more than one variable in it, but they're all 2 whole number powers, so it's completely allowed. The degree of a term is the total number of letters I see in there. So I see 2 x's and a y in that first one. So what's the degree of that term? I see 2 x's and a y. So it's the 3rd degree term. What about this guy? 4th degree term. The degree of the whole polynomial is the highest degree I see. So that binomial would be a... What's the highest degree I see? 4th. So that whole polynomial would be a 4th degree binomial. Sounds vaguely like a karate competition or something. I'm a 4th degree binomial. The world's lamest belts. Sorry. Is that cool? Did you guys get that? So what's the degree of each term here? You can do this. What's the degree of that first term? Good. 11th degree. degree is easy. Fifth degree. I love it. Go with your gut. How many variables do you see?
0.
None. So it's a 0th degree. Right? So that's the degree is just how the total number of letters I see. So if I don't see any, it's a 0 degree. That tells me it's a constant. That's really what that means. A 0 degree polynomial is a constant. 11, 6, whatever the hell. So what's the degree of that whole? Yeah, so this would be an 11th degree trinomial. Cool. Okay. So that's not difficult, right? It just takes a little getting used to how to determine stuff like that. Yes, ma'am.
Why is it? Oh,
Because the degree of a polynomial is the highest degree that I see. See, these are all connected inside of a term. That's why I end up adding these together.
so they're both the highest. That's the thing.
The whole thing would be the highest.
Okay.
Because, let me see, like this guy, when x gets really, really big, which term is most important? Does minus 3 matter if x is 18 billion? If I have $18 billion and $3 falls out of my pocket, I won't be as concerned as I would be today if it drops out. So if x is 18 billion, the most important term in here, the most heavy term would be this guy. So saying it's a second degree trinomial kind of tells me how quickly it's going to grow, the most important part of it, the part that's going to grow the quickest. Maybe. Yeah.
How come it's 3, that's 4th degree is the xy together, or is the 3 with the y? And how come that 4th degree?
So this xy cubed is, of course, x times y.
It's pretty much like an
Right.
imaginary.
So this is x,
like a 1, right?
y. Cool. Because that 3 obviously is on the y. So I got 3 y's. You with me? I got x times y cubed.
Oh, you're making up the letters. Okay.
Because that's what it is. It's not something I'm choosing to do. It's what it is. Cool?
Why isn't that top one to the 3rd degree though? If there's the x squared, then you have that 1x divided by 5.
This term
Yeah.
is second degree. This term is first degree. And this term is... So what's the highest degree I see? Second degree.
Oh, you don't combine them?
No. Because they're plus, right? If you really get down to it, and don't make more of this than it is, but if that y was an x, then wouldn't this be x cubed? So when I talk about the degree of a polynomial, I kind of think to myself, if I allow all the variables to grow at the same rate, the whole thing would grow how quickly. And this would, This one would determine, because it's growing the fastest. It's 4th degree piece. So that's what I want to tell somebody. I got a 4th degree binomial. Oh, so you're telling me the biggest one and how quickly it's going to grow that piece? That piece is going to way beat this piece. Right? If I make x and y 18 billion each, this is going to be way bigger than that. Kind of with me?
Yeah.
Specifically 18 billion times as big as that. Right? So telling somebody it's a 4th degree is going to tell me which term is the heaviest term. It's a quick way of telling me that. Yeah?
Why is knowing everything important?
Just so, 2 reasons. It kind of helps me figure out how quickly the thing's going to grow or shrink if I make x really big negative. But it also gives me an idea of the shape. And of course the shape we're going to learn a little bit more about later. Because all about how many times is it going to turn, how many turning points does it have, that kind of thing. That's very good to know, especially if I'm talking about my profit. If I'm like this much and say that's a good place to be, and I didn't know there's a whole other place I could be to make the profit even bigger because I didn't know how many turning points there were. That kind of sucks. So if I know the degree of it, I know how many turning points it has. Cool. Okay. All right, that is a bit deeper than I wanted to get into that. Keep that very superficial for right now, because most of the real aspects of why these things are important come into play later. The shape of it, how to compare it to other polynomials, things like that. We're not too concerned about that yet. Now, beyond the terminology, the first section, section 9.5 in the white book, In the blue book, it's chapter, I think the first part of chapter 5. The rest of this is really just adding and subtracting polynomials and multiplying. What is one thing I was going to say? Oh. And before I get into that, let me real quick review of exponents before I get too far along. Very quickly. You know, x cubed means x times x times x. Right? So it's really just kind of a quick way. Some guy already did this. Right? He said, let's make x plus x plus x 3x. So I don't have to write the damn thing out. So if I have 80 x's in a row, please, dear God, let me just write 80x. And everybody called everybody because they had cell phones back then. So then this guy on the other side of the world is like, screw you, dude, man. What the hell am I going to do with this shit? I got all these x's in a row. I don't want to write those all. So he decided another place to put the 3. So now everybody understands. So one part of that is the way that we do all of mathematics had to be decided. It's a complete human invention, a way of describing what we see and what we can work with. That 3 is there just because somebody said, hey, let's put it there. And somebody else said, that sounds good. And somebody else said, I don't like that. And they killed it. Stuff like that actually happened. But, so, if I have x cubed times x to the 7th, that, of course, will be x to the 10th. Because now I just have 10 links in the chain. Not a big deal. So all the properties of powers come from this. Math people being lazy or frugal with their time, whichever way you want to look at it. So, of course, what's x to the 7th over x cubed? Exactly, because you're cutting 3 links off the chain now, right? If this is linked by multiplication and I'm dividing some of it away, it's going to go away, and I'm going to have fewer of those things. So I subtract when I divide. Not a big deal, right? So then, what happens when I do this?
6.
That's when I multiply, right? Because what does this really mean? 3 groups of 2 x's are, of course, 6 x's. So this would be x to the 6th. And we all know the quickest thing, the thing our brain does evilly is it mixes up when to multiply, when to add. Yeah, right? Because when we see this, we say, Jeff, I'm multiplying, Jeff. But then I tell you, there is actually no 2 in there. There's no 3 in there. There isn't. And you go, you sure you feel better? But there is no 2 in there. There is no 3 in there. There's 2 x's and 3 x's. These numbers aren't numbers. They're just telling me how many x's I've got. So when I see that, I got 2 of them, 3 of them, so of course I got 5 of them now. Not a big deal. We are still going to make the mistake sometimes, though. It's hard to keep our brain fully going along with us. So what about these 2 weird little things? What's x to the 0 power? 1. And I think I showed us why before. 5 minus 5 is 0, but something divided by itself is 1. Cool. 0 to the 0 power, by the way, is horrible. It's not undefined, it's indeterminate. Something even worse. That's the most I'll talk about that in this class. Right? 0 to any power is 0. Anything to the 0 power is 1. So 0 to the 0 power is like, what? It's like an unstoppable force, meaning an immovable object, right? You guys ever heard of that? Has anybody ever heard that phrase before? I'm the only one. Anyway, the thing to know about that is that sucks. You don't want to mess with that. What about this?
1 over x.
Yes, good. 1 over x. Negative powers mean flip. Did I show you why yet? I can't remember.
Yeah.
I did? Good. All right. So the rest of this is really just like terms, but also take a quick second here and multiply this for me. So this is not really FOIL, but we sometimes just call this FOIL just as a catch-all. All I really have to do is distribute each piece of this one at a time, right? That's the idea. So I get x cubed
Plus 8
plus 8x squared minus 7x
minus 4x
minus 4x squared
minus 32x
minus 32x
plus 28.
plus 28. And then I just put my like terms together. Now comes the nice part that a lot of you might not have seen, and that is how to divide polynomials. If I were to divide x cubed plus 4x squared minus 39x plus 28 by x minus 4, can you tell me what we should get? Yeah, you have to use long division, but I'm going into this problem already knowing the answer. 3 times 2 is 6. So what's 6 divided by 3? 2, because 2 times 3 is 6. This times this is that. So what's that divided by this? That, right? So I like to go into something knowing the answer, especially when it's something that some of you guys might have never seen. But I think most of us probably have seen long division, maybe. Maybe a few of you guys. So let's see how this works. It just sounds good, doesn't it? Long division of polynomials. It just sounds like it's going to be awesome. Now, I don't know if there's anybody in here who sets their division up a different way. Very often I have students who come from Europe or other parts of the world, and not everybody in the world divides this way. So sometimes it's a hurdle for these students. I always forget how that other setup is.
Can I ask you a quick
Yes.
question before we continue? Because I'm trying to kind of remembering how the whole how the numbers turn to negative and positive, like positive 8 and negative 4. That's a positive because the 8 is bigger, right? I mean, yes.
Yeah, when you put two
Yes.
numbers
Because
together.
because the 8 is bigger,
Yeah.
that's why it's
So if they're opposite signs, you subtract, and the answer is a sign of the biggest one.
And
If
with
they're the
7
same sign, you add and you put the sign back on.
And with the 7 and the 3 is because both of them are negative?
Both of them are negative. It's like I owe $7 to you and I owe $32 to you, so overall I owe $39. Yeah. Cool. All right, so here. How many guys have never seen this until now? Anybody? A few of you. Okay. So x goes into x cubed, x squared times. You with me? He's really asking yourself, what do you have to multiply this by to get this? That's what that means to go into that. And so now I say x squared times x cubed. X squared times x is x cubed. X squared times negative 4 minus 4x squared. But then, of course, what do we do when we divide? We subtract this. So what I really do when I have expressions is I just change the signs. Because that's what subtraction would do. It would change the signs. Those go away. Here I get 8x squared. Bring down the next guy, just like we would in normal long division. X goes into 8x squared.
8x.
Yes, sir.
You go
Plus 8x.
the step from you got x squared, and then how did you get the
X squared times x. X cubed. X squared times negative 4. Negative 4x squared. And then I change the signs because when you do division, if you did 7 goes into 39, right? You would say 5, multiply, subtract. So you just change the sign on that next step, right? Okay, good. Easiest thing to forget when you're doing this. Then you bring it down, just like I would, if there was more to this problem, I would bring down the next thing. Right? So now I just bring down the next thing. X goes into 8x squared. 8x times, that's what I'm kind of missing. Right? So 8x times x. 8x squared. 8x times negative 4. Negative 32. Change the signs. Okay, maybe. These go away. Negative 39 plus 32. Negative 7x. Bring down the last guy there. So now x goes into negative 7x. Negative 7 times. Negative 7 times x. Negative 7 times negative 4. Oops. And then you change the signs. No remainder. Cool. And so did we get the right thing? Yeah. Right, we went into that knowing what the answer should be. We just went into it not knowing how to do it, maybe, some of us. So that's how it looks. It looks disgusting.
But
Yeah.
it's no remainder, isn't it? 28 plus 28?
28 minus 28 because you have to change the signs.
Oh.
Yeah. Okay. I only gave you a couple. Actually, I only gave you one problem like that. Let's do this. You want to take like a quick 10-minute break, and then we'll get into factoring? All right. Let's come back about 35 after.